weld. Are we good with this? Hello? So the first thing that we need to do is find out what is the center of gravity for the weld. Okay, so if there are any questions, please feel free in talking about it and letting me know. I'm just trying to show a conversation. Yeah, recording has started. Yeah, everything is good. Okay, so if there are any doubts in what I'm saying, please feel free to find out and let me know. Okay, so the first thing that we need to do is we need to find out what is the center of gravity. In this case, because of the symmetry, the center of gravity in the y-axis will be along the x-coordinate axis, and uh, because it's symmetrical, and the center of gravity in the x direction can be worked out, which is just going to be integral a dx by a. So if you take the center here, and if you say that this is 8 inches, and the overall weld size will be 8 and 8, 16, and 12, which will be 28 inches. So you'll have a 28-inch uh, weld size, total weld size. So your total area will be 28 into whatever is your thickness. The thickness is uniform, so it doesn't matter. So 28, and your integral a x bar will ax will be 8 into 4, that's 32, into 2, that is 64, and so your shift from your axis will be 64 divided by the total area, which will be 12 and 8 and 8, that's 28, to 64 divided by 28, and that would end up giving you uh, whatever is about a little more than 2 inches or something, which will be your uh, x bar. Is this making sense? Is this okay? So 2.28 inches will be your x bar. Is that good? Array, mute yourself, na? Yeah. Okay. So is that okay? Is this making sense? So the x bar will be about 2.28 inches. Now, yeah, that's the one that says 2.286 inches. Now, the ultimate load here, every code has a different set of partial safety factors. Here in this code, they're using 1.2 for dead load and 1.6 for live load. But in our case, we'll typically use 1.5 and 1.5. So it doesn't make a difference. But anyway, so the PU which has been calculated here has been 60 kips, and the PU which we would have calculated would be different from this. But that is just what are the safety factors you use. It does not change in principle how the design is actually being done. So what is the moment going to be? The moment will be 10 plus 8, that's 18, 18 minus 2.285, uh, which will be 15.714, and that you multiply by your PU, which is 60 in this case, so you'll get 942.85 as your moment. 942.6 kips inches as your moment. That ends up as becoming your actual moment in your system. Are we good with this? Now, the force which is acting in the y direction. So your entire weld will first get a shear, which will be a shear in the y direction, which will end up as becoming just this force divided by the total length. So you'll end up getting 60 divided by 28, or 2.143 kips per inch as your shear in your y direction. So this is your fundamental shear in y direction which will happen. Now, there are two ways of doing this analysis of welds, and only one of them is possible to be done by hand. So we are just going to be concentrating on that. We will, at the end of this, tell you what is the other analysis and give you an indication of how it can be done. But it can never be an exam question because it is not something which can be done by hand.
एक्सक्यूज मी सर,
Yeah.
सर कोई किक कर रहा है बार बार मीटिंग के बाहर.
हाँ नो, मैं कुछ नहीं कर सकता यार, बिकॉज मैंने वो कोशिश किया यहाँ पे उसमें वो ऑप्शंस में जाने के लिए, और ऑप्शंस में वो यहाँ पे जो है दे आर व्हाट यू से it's giving, I'm not able to go there because of something wrong with the website right now. So I've been trying to go into the options, and let me try once more actually.
ठीक है.
Something went wrong, reload the page, or if this keeps happening, try again later. So I'm sorry. I mean, short of this, there's nothing else I can do. If somebody keeps kicking you, keep coming back in. I think that's all you can do.
Okay.
Yeah. I mean, I'm sorry, there's nothing I can do about it. Okay. So the shear in Y, if somebody kicks me, you know, I'm not going to come back. Okay. So, so the shear in Y is 2.143 kips per inch, which is the fundamental shear. This shear is the shear which is coming because of the force itself. Okay. After you've got the shear which is there for the force, we're going to calculate what is the shear which is going to be coming for the moment. The moment is going to be Ix plus Iy.
Sir, somebody muted you.
So if you look at the polar moment of inertia, the polar moment of inertia about the x-axis is going to be 1 by 12 b t cubed plus a y squared, which is I mean, that's fundamentally just the mm, calculation. Okay, so the inertia in x is going to be 1 by 12 into 1 into 12 cubed plus 2 into 8 into 6 squared. So you get 720 inches raised to 4. And similarly, the polar moment of the rectangular moment of inertia in Iy is going to be 195. So the total J is going to be 195 plus 720, which is 915 inches raised to 4. No, this is simple. This is just a moment of area. So now the second thing is that F1 is what we are trying to say is because of the force, and F2 what we are saying is going to be because of the moment. So F1x is going to be 0 because there is no force in the x direction. F1y we have calculated as 2.143, which is there everywhere. Now F2x is going to be my by j. Now the F2x is going to depend wherever your y is maximum is where you're going to get F2x as maximum. So in this case, y is going to be maximum at the top and bottom. So you get 6.181, which is the maximum F2x, and F2y is wherever your x is maximum. To be the so the x maximum in this case will be at this point here. So if you look at it from here, the distance is going to be 8 minus 2.26 or whatever it is. So that ends up as becoming F2y, which is 8 minus 2.286 into 942.6 by 915. So you get F2x. Now you do a vectorial addition of this, which is 6.181 squared plus 2.143 plus 5.886 whole squared, which gives you 10.13 kips per inch. Now this is the shear which is going to be coming in the system, and you just need to now and it is per inch. So you just need to know what is the strength of the weld, and once you know the strength of the weld, and you know what is the shear coming on it, all you need to do is decide whatever is the size of the weld. So I think that is a very straightforward thing, because once you know what is the shear coming per inch or per unit length, in this case we are looking at inch, so it's inch. Otherwise, if it were looking at mm, it would be this per mm or whatever. And then once you know what is the shear coming per mm, all you need to do is figure out what is the strength of the weld. And once you know the strength of the weld, decide the size, or if you know what is the size, decide the strength. So yeah, that's your calculation which is being done in this case. Is this generally clear as to what is happening here? So what we have done here is we have done three things. Going back here, first we have found out whatever is the CG of the weld. So actually first what you have done is you have assumed a weld, in the sense that you have assumed that this weld is going to be all around. After you have assumed that this weld is going to be all around, you have found out what is the CG of the weld. Once you found the CG of the weld, you have found out what is the shear per unit length, which is based upon the force alone, and it's in the y direction. Then you have found out what is the moment, because the moment is, once you know the CG of the weld, you know what is the moment coming on the weld. And once you know the moment coming on the weld, you have found out what is the shear in x direction maximum. You found out what is the shear in y direction maximum. You have done a vectorial addition of that. And then this ends up as becoming a value, which is the actual strength that you need to design for. And based upon this, you're designing whatever is the size of the weld that you need. Is this making sense, guys? Is this okay? Is this all right? Guys, is this making sense?
Yes, sir.
Fantastic. So yeah, I think yeah, I get your point, Apan, that I think your next class, either I will hold it on if I can change the setting, I'll do that, and if I can't change the setting, then I'll hold it on WebEx. Of course, we can make a request to the disturbed soul who's trying to disturb the meetings by saying that do something, man. You can figure out your life. You can figure out something else. तुम्हें लोगों को पेन देके अगर हैप्पीनेस मिलता है तो यार कुछ तो प्रॉब्लम है ना, तुम्हारे अपब्रिंगिंग में कुछ तो यार कमी रह गई है ना? शायद प्रॉब्लम तुम्हारा नहीं है, शायद प्रॉब्लम तुम्हारे पेरेंटिंग का है, बट जो भी है, कहीं पे भी प्रॉब्लम है, कहीं पे तो प्रॉब्लम है तुम्हारे में. Are we good with this? Is this making sense? So the concept here, and this is called an elastic analysis, because what you're doing is that you're actually trying to figure out that what is the maximum, at what point is the maximum force reached. And what we are saying is that once the maximum force or the maximum stress has been reached at one place, this point is what we are saying is the failure point. But that's actually not true, because in reality what happens is that once you end up getting one place which reaches its yield point or something, then what happens is that it starts yielding. That point starts giving you a local yield condition, and then the stress transfers at other places until you get a yield which happens at a large place. You've done this now, in the sense when you did your plastic analysis, and when Rajiv introduced this course to you, he must have talked about you about the difference in the stress block, which is an elastic stress block and a plastic stress block. Did he do that? Guys, somebody?
So please repeat.
When you started this course, was there a talk about the difference between an elastic stress block and a plastic stress block?
No, sir.
That like, for example, if you look at a beam and you look at flexure, then the elastic limit is reached when either the top or the bottom reaches its yield point. Okay.
Yes,
If you bend this beam beyond this, what happens is that your yield point starts becoming, instead of a triangle, it becomes a trapezium, and slowly tries to become a rectangular stress plug, because the yield progresses from the outermost point towards the neutral axis. And the actual failure of the system happens when your entire section is in yield and not just when the outermost fibers are in yield. Is this making sense?
Yes, sir.
So this is the difference between an elastic analysis and a plastic analysis. That the elastic analysis assumes that once yield is reached anywhere, we are calling that as failure. The plastic analysis says that after the yield has reached, I mean, like, even if some part of the thing ends up giving you a local yield, it is not considered as failure. Failure happens when the entire section comes under a plastic limit. Okay, so the analysis that we have just now done about the weld is an elastic analysis, because we are saying that the minute some place of the weld ends up reaching your yield point, we are saying that this signifies that the strength of the weld is this. The actual strength of the weld is going to be much more than this, because once it reaches yield point, this place will give you some form of a local yield, and the yield will slowly develop over the length of the weld as more and more sections start coming under yield criteria, and your actual failure of the section will happen at a much later point than when the first point of coming into yield has happened. Is this making sense?
Yes, sir.
Okay, so what we are right now doing is the elastic analysis. Okay, now in a later lecture I'll talk to you about the plastic analysis, and I'll also mention and I'll also show you why it cannot be done by hand, because it's an iterative process which involves finding out what is your instantaneous center of rotation. Have you come across this concept of having an instantaneous center of rotation?
No, sir.
No, no. So I think you'll just have to take my word for it for now. But I'll also put in a small kind of some handwritten notes which talk to you about what the instantaneous center of rotation is, if you want to know more about it. It's not part of the course, but if you need to know more about it for your personal information, I'll just put this in place. Does that sound okay to you?
Yes, sir.
Okay. So have we understood this right now as to how this how you do a elastic analysis of a weld? By the way, have you done this for bolts? This concept of mm, in-plane moments in bolts, bolted connections, or is welds the first thing that we are doing?
So we did the eccentric connections for bolts.
Okay. So in bolts also you would have done it in a similar way. Now find out what is your moment of inertia, find out what is your T, find out what is your centroid of your bolts, and
Yes.
then find out what is your TC by J, and then do the same vectorial addition that you're doing here. So in principle, what you're doing here for weld is exactly similar for what you're doing for bolts. And in bolts also, you would have found out that what you have done right now is an elastic analysis, and that there is something called a plastic analysis, which is much more than this. And there are some rules for that. There are some what is the distortion of the section and what is the deformation of the section and things like that. So have you come across, has Rajiv touched the plastic analysis part of this in bolts?
No, sir, we didn't discuss the plastic analysis of bolts.
You just did the elastic part of it,
Yes,
right?
sir.
Fantastic. So then I think that's what we have done here. We have the elastic part of it for welds. And at some point of time, when we do the plastic part of it, we'll do it for both bolts and welds together. So then we can also see how bolts are being looked at when you look at a plastic action and how welds are looked at when you look at a plastic action. Is this okay?
Yes, sir.
So is this generally cool? Because I think this is it. Because beyond this, everything else is just what is the strength of the weld, and once you know what is the shear coming in, finding out the strength of the weld is something that we have already done. So you just need to plug it in and find out what your solution is. Is this making sense, guys? Is this okay? Fantastic. So ये समझ आ रहा है ना? Is this ये ठीक लग रहा है ना तुम्हें? अभी तक तो ये अच्छा अच्छा anyway, so ये ठीक लग रहा है? By and large, हमने जो किया. So I think fundamentally, if you look at the code, and let's take a look at the code for connections, and we can take a look at, once we have connections, you can just go down a little bit and take a look at the bolts, and you can go further down and you'll take a look at the welds and friction type bolts, and then you go further down and you take a look at the trying forces welding. And effective length, EFO, effective area, side welds, long joints, clear spacing, fillet welds, individual forces, combined bearing and shear, and I just wanted to see design of connections. Yeah. Yeah, analysis of a bolt and weld group subject to in-plane connection. Now, this is exact. This 10.11 is the codal clause of what we are doing. That the connection plate shall be considered to be rigid. In case of a group pure couple only, the instantaneous rotation of center coincides with the group centroid. In the case of an in-plane shear force applied at the group centroid, the instantaneous center of the rotation is infinity, and the design force is uniformly distributed through the group. This is what we did. So if you look at this particular clause, this is exactly what we have said, is when we have said that the shear force is uniformly distributed throughout the group. So this comes from this particular clause in the code, which says that the instantaneous center of the rotation is at infinity and the design force is uniformly distributed through the group. The design force of a bolt or design force per unit length shall be assumed to act at right angles to the radius from that point to the instantaneous center and shall be taken as proportional to that radius. Now, fundamentally, this is the alternative analysis. Subject to in plane and out of plane loading. Yeah. Force calculated in the most stressed or highest bolt shall satisfy the strength which is appropriate, which is the kind of analysis that we are doing. On the other hand, a plastic analysis is also something that the code allows you to do. The thing is that for the plastic analysis, there's a general method of analysis, there's a special alternative analysis. है यार, देखा हुआ है. Now, all of these are valid. The only thing is that when you're looking at it as an instantaneous center of rotation of the group, and you're trying to figure out what exactly is your what exactly is your failure point. The code is actually doesn't say that the design force shall be assumed at right angles. All of this is fine. The code doesn't say that you need to take just the most stress bolt as your, so in the general method of analysis is not that you have to take the most stress code, but the alternative analysis is that a design force may be alternatively determined by considering as an extension of the connected member and proportioning the design to satisfy equilibrium between the elements of the connected member, and the force calculated in the most stress code or the highest force which shall satisfy comparisons of 10.3, 10.4 or 10.5. So one of these ends up as giving you what is the elastic method of analysis that we are talking about, and the other is talking about that it is possible for you to also do it by considering a plastic analysis system. So are there any questions that you have on the analysis system that we have been actually working on till now?
Sir,
Yeah.
so how about out of plane loading of weld group? Like twice here written for a weld group out of plane loading.
हाँ, आउट ऑफ प्लेन हमारा एनालिसिस करना बाकी है बेटा, अभी हम
Okay.
इन प्लेन कर रहे हैं.
Okay.
I mean, see, the out of plane analysis will have a tension compression component to it in along with the shear component to it.
Okay.
Okay, like for example, when you did an out of plane analysis of a bolt group, okay, if
Yeah.
when you did when you did the in plane analysis of the bolt group, you found out that the in plane analysis is just shear, and it's just shear in different directions. You know, you got shear in X and shear in Y, and then you do vectorial sums. The out of plane analysis, even when you did it for a bolt group, ended up as giving you a shear because of the force and a tension compression component because of the moment. So you will get a similar kind of an action because of in your welds, but that we haven't done yet. In the sense, right now what I'm talking about is just the in-plane component of it. Is this okay?
Yes, sir.
So ये जो out of plane वाला जो portion है, which is this part, is not something that we have talked about yet. What we have generally talked about as of yet right now is just the in-plane part of it, and these are the codal clauses that we are talking about as a part of your analysis of a bolt weld, which is an in-plane component. Okay. Now, typically in-plane ends up as becoming usually a far better way of doing an analysis than an out-of-plane, because the simpler the way the forces are actually behaving, the more robust is your actual connection. तो आउट ऑफ प्लेन कर सकते हैं, हम आपको एनालिसिस भी करके दिखाएंगे, but out of plane is never considered a good, I mean, it is something that you do if you have to do it. It's a good design is actually something which can avoid out of plane actions of bolt groups and weld groups. Is this making sense, guys?
Yes, sir.
कि जहां तक हो सके in plane is a far better way of conducting forces, because your actions are simpler ना, कि आप only shear में काम कर रहे हो, दूसरे में तुम shear में काम करोगे, कहीं पे bearing होगा, कहीं पे compression होगा, कहीं पे tension होगा. It just starts making things very very complicated, isn't it?
Yes, sir.
So and because it gets complicated, it fundamentally also means that जितना चीज complicated हो रहा है कोई भी डिजाइन में, उतना तुम्हारा actually उसके ऊपर कंट्रोल जो है ना वो कम होते जाता है.
Yes, sir.
So as far as possible, you should try and keep things simple, because simple things are also more reliable and more controllable than complicated things. Is this making sense, guys? So I think I'm just going to stop here and ask you whether there are any questions that you have for the things that we have done till now, and there are any ideas or anything that you can discuss. आपको कोई thoughts हैं? Is there something that you'd like to talk about? If something which is not clear? Are we generally good for understanding the in-plane actions of weld?
It will come back tab, shift tab means it will come back.
I'm sorry?
సందీప్ నీ ల్యాప్టాప్ కనెక్ట్ చేసావా? సంజయ్ కూడా కనెక్ట్ చేసిందా?
Is there anything you guys would like to talk about? Any questions you have? Then in the Monday class, then we will start with the next topic, which will be the action of weld groups to out of plane loading. So are we good with the in-plane loading that we have done till now? Any questions anybody has about in-plane loading, or is it okay? Somebody guys, some kind of a feedback on this? Do we accept that this is okay and then we carry on with the out of plane loading from next time? Guys?
So I think you should call some directly ask by name to someone who has everybody understood it or not.
Yeah, I should ask my name, is it? Okay. Then
Yeah.
Rahul Gupta, have you understood this?
Sir, I have understood it, but I have literally studied it priorly before. A little, though a little. The
Yeah.
others are new to it, so they should respond more.
Right. So let's ask a few random people. Rishabh Sharma. Divyansh.
Yes, sir.
Yeah. So have you understood what we are talking about, Divyansh? Or oh, Rishabh is talking, right? Okay. So Rishabh, what about you? Have you understood what we've talked about? Rishabh.
Yes, sir.
Have you understood this topic about in-plane forces and weld groups? Is this clear to you as to what we have done? Jaya Rawat.
Yes, sir.
So, is it clear to you as to what we have done, Jaya?
Sir, I have understood.
You've understood. Fantastic.
Yes.
What about Divyansh? Divyansh, have you understood?
Yes, sir.
Sure.
Yes, sir.
Any questions that any of you have? Divyansh, do you have any questions?
No, sir.
Do you have any questions? Is there anything which is unclear which you'd like to understand better?
No, sir.
Fantastic. So guys, I think I'm going to leave it at this point, and next class we will start talking about welds with out of plane actions. Okay, thank you very much. Have a great weekend, because I think weekend is started. At least for me it is. So I think this is the last thing that I'm doing, and now I'm looking forward to 3 days of oh my God, absolute peace and quiet and doing whatever it is that I'm doing. So same with you guys. Go do whatever you do on a weekend. Enjoy yourself. Have fun. Yeah.